So in this video, I want to answer this question, but using the concept of linear transformations. Okay, so I'll assume that I have a matrix A with columns A1, A2, all the way to AN. Okay, just for simplicity, let's assume or start with the case. That's right. Let's start with the case where n is 3, just to show you how the argument works in this case, and then we can generalize it to the case where there are n columns. So let's start with the case where n equals 3. So in a proof, you can simplify the assumptions, or for example here we can simplify the statement by assuming that we have a 3 by 3 matrix, and if we come up with an argument that's general enough so that it can be adapted to n by n matrices, we can just mention this at the end of the proof. So it's not too bad to consider a specific case here, and then to have a proof that's general enough so that it can be adapted to the more general case. Okay, so therefore A would be the matrix with columns A1, A2, and A3. Okay, and again here I'll make an extra assumption. I'll assume, for example, that it's A2, that's the column with all zeros. So let's assume, and again here the goal is just to simplify the argument, but not simplify it so that it would not apply to any matrix. So I want to keep an argument that would still apply even though it would be A1, that would be the column with all zeros. Okay, and again here it's just so that the reader can more easily follow what's going on, and after that I'll just say that without losing without loss of generality, I can extend my proof. So therefore A is now the matrix A1, 0, A3. Okay, I'll put an arrow just so that you remember that this is the vector of all zeros here. So what does that mean in terms of linear transformation? So this matrix A would correspond to a linear transformation. So we call that the standard matrix. It's the standard matrix of the linear transformation which sends I onto A1, J onto 0, and K onto A3. So that just means T of I is A1, T of J is 0, and T of K is A3. So the if you were looking at where I, J, and K get sent, actually when we look at the transformation T, so maybe therefore I'll write here, therefore T of X, which is AX. Okay, remember this is a linear combination. This matrix vector product is a linear combination of the columns of A. Right? Because when we do, okay, that's because when we do AX, what are we doing here? We're doing A1, A2, A3 times maybe x1, x2, x3. This matrix vector product, we can actually write it in the form x times a1. I'll write an arrow here so that remember a1's a vector, x1's a scalar, plus x2 a2 plus x3 a3. Okay. So what we see here is that our matrix vector product is just going to give us the span of the columns of the matrix. Okay, but the thing is that this vector here is 0. Okay, so the span of my columns is just the span of a1 and a3. So that's just the span of a1, a3, which is a plane, right? Because it only has two, well, it's a plane or a line, but if a1 and a3 are linearly independent, it's a plane. If a1 and a3 are parallel, it's a line, okay? Which is either a plane or, well, assume they're non-zero. If they're all zeros, this would just be the point 0. A plane. So it's a plane, either a plane or line. I could even write or a point. Okay, in R3. Okay. So, but the point is that its dimension is clearly less than 3. Its dimension, its dimension is less than 3. So that means that when I start with x and I do the linear transformation t, okay, I get back ax. Okay, initially this is in R3. Okay, so the x is in a space of dimension 3, which has dimension 3. But this guy here, has dimension less or equal to 2. Okay, so ax lies on an object that has a dimension less or equal to 2 because it's either on a plane, a line, or it's just a point. Which, if it's a point, it's just the point 0. And then that shows you can't go backwards, right? Because you can't go from a space of dimension 2 to and generate a space of dimension 3 with linear transformations. Okay, that I've shown you on a comment, I think. Yes, on a comment on Moodle. Okay, so since with a linear transformation, we cannot map a point, a line, or a plane onto R3, then this transformation has no inverse.